Good morning, everyone. So today I'm going to present my paper's presentation entitled Towards Seamless Communication in Capillary Networks. Um, the paper is presented by me, Aliaa Walid. Uh, so for today, first I'm going to give an introduction about the topic, then I'll talk about the related work, then I'll phrase the problem statement and propose my solution framework. Then I'm going to talk about the simulation setup and results, and finally the conclusion and future directions. So I'll start my presentation by giving a brief introduction about the capillary network, just to clarify the whole topic. So capillary network initially came from the concept of IoT, which is the Internet of Things. So let me first introduce the conventional IoT structure, which is the umbrella of my topic. So the IoT sense a system is divided into 5 layers, namely the perception layer, which is about gathering the data from the sensor nodes or the sensor devices. Then the sensor data is then transmitted to the middleware layer using the network layer, which is made of gateways using network technologies like Bluetooth and Wi-Fi. Uh, then the middleware layer, which is responsible for the data storage and decision taking and information processing. And then we have the application layer, where the collected and analyzed information is presented to an end user using the application layer, where we have the smart applications. And finally, we have the business layer, which is mainly about creating the business models. So the following structure corresponds to the layers that I just introduced. So previously there were different kinds of network where each network works with its own technology, and then the gateways collect the data specifically from each network. This has created a limitation in the connectivity and the reachability, where the gateways cannot deal with new nodes or sensors. It cannot understand them, and this has created a communication issue for new sensor nodes with new technologies. So currently, due to the heterogeneity and the increase in the heterogeneity of the type of the sensor data, this has forced the research to try to find a suitable solution for the problem of the heterogeneity and the compatibility. And therefore, a new layer has been introduced, which is the capillary network layer, which works as an endpoint predictability layer, which has helped in solving these problems, and it is made of smarter gateways, which are called the capillary gateways, which is my research area. So let us talk about the capillary network. So a capillary network is like a local area network that uses short-range radio technologies. These short-range radio technologies could be Wi-Fi, Bluetooth, Zigbee. It consists of the sensors that are connected to the capillary gateways and then up to the cellular network for global connectivity. And this capillary network can utilize the key capabilities of the cellular networks, such as the network management, the ubiquity, and then we can connect efficiently with other ubiquitous networks. Then let us talk about the related work. So I have reviewed about 32 papers about the ubiquitous networks, the 6G networks, the capillary networks, and the seamless communication, which is my main paper scope. So let me talk about some of the seamless communication approaches that has been proposed. First, we have the first paper. It has proposed an autonomous detection of wireless technology with secure end-to-end communication and transmitting power control with energy efficiency. It has proposed this solution with using machine learning based classifier with feature extraction. However, this system lacks hardware simplification and a robust security protocol design. Then we have the second paper, which has developed a distributed scheme for achieving energy efficiency in seamless communication and formulating a multi-device IoT system. In addition to proposing a game theoretical approach using a Nash equilibrium for reaching an enhanced transmit power for devices. Then we have a spectrum analyzer technique to differentiate between different standards and depends on the bandwidth and the frequency shape. However, it did not succeed in the narrow band segments such as the IEEE standard 802.15.4. Um, so, despite the efforts, there are still challenges in this IoT concept, which needs further enhancement. And this is mainly my research gap, the seamless communication in heterogeneous networks. Uh, so let me phrase the problem statement. In the currently available research, none have presented a comprehensive and optimal solution for the problem of how to enable gateways in capillary networks to seamlessly communicate with different sensors, and these different sensors will be using different kinds of wireless technologies in the heterogeneous IoT networks. So let us talk now about the solution, my solution framework. So the solution framework consists of three tiers that I'll be presenting now. So firstly, we have a pool of different sensors with different wireless technologies, such as Wi-Fi, Bluetooth, and Zigbee. And these sensors would be connected with the capillary gateways, and this is the first tier of our proposed framework, which is responsible for collecting the data from the sensor nodes and then announcing to tier 2 gateways the type of data that it will collect. Of course, this type of data will be according to the central manager, which is responsible for the policy. However, these two tiers, tier 2 and tier 3, are not the main scope of this paper. The main scope of this paper is mainly about tier 1 gateways, which is the capillary gateways, by introducing a seamless communication protocol. And this seamless communication protocol will be integrating a gateway will be integrating all the technologies, and it can deal with different kind of sensors with different technologies such as the Wi-Fi, the Bluetooth, and the Zigbee. So this is the on the right side we have the stack of the protocol stack of the capillary gateway proposed. Uh, where it can deal with several network technologies, the 802.11 standard, the 802.15.4, and the 802.15.1. The reachability here represents, of course, the possible connectivity between the capillary gateways and the IoT devices by presence of a radio signal with sufficient signal strength. Here is a screenshot of the simulated network topology. As we can see, we have 4 ranges with 4 capillary gateways. The first capillary gateway on the left side is the gateway proposed with and the modified one with all technologies. It can deal with Wi-Fi technology, with Bluetooth, with Zigbee technology. And then we have the second capillary gateway with the Wi-Fi technology only, and then the Zigbee only, and finally the Bluetooth. This topology, we have the sensor nodes with different types in each range, and of course the sensor data is collected from the sensors to the capillary gateway, and then up to the intelligent gateways, then to the central manager, to the cloud. Of course, we are here in this paper mainly focusing in the communication between the sensor nodes and the capillary gateways. As for the simulation parameters, this is the simulation parameters for my simulation. Then for the performance matrix, we will be measuring our and evaluating our simulation according to the IEEE standards in terms of the network operation and performance and the quality of service. We are going to measure the total number of requests in the network, which is the number of packets that will be received, the packets that are permitted, the packets that are denied, the packet loss, the power consumption, the throughput, the end-to-end delay, and the jitter, and the number of devices in reach of a gateway. So here we have the throughput. Firstly, we are going to measure the throughput between the gateway, the modified gateway, and the Wi-Fi only gateway. The Zigbee, the second screenshot for the modified gateway as well, and the Zigbee only gateway, and finally the modified gateway with the Bluetooth only gateway. Of course, the throughput is computed by examining the packets transmitted across the transmission medium over time. And as shown in the figures below, the throughput has been enhanced at the modified gateway by average 26% for the Wi-Fi, the ZigBee average 5%, and Bluetooth 50%. Of course, the throughput is measured in megabit per second. As for the simulation results for the packets received, as we can see here in the first chart, we have the 4 ranges, range 1, range 2, 3, and 4. For each range, for each capillary gateway, 1 and 2 and 3 and 4, as I have shown you previously in the simulated topology slide. As we can see here, we are capturing the packets sent and the packets received at the capillary gateway for the Bluetooth sensors only. And as you can see, the range 1 capillary gateway, which is the modified capillary gateway, it has received all the Bluetooth packets. However, for range 2 and 3, it did not receive because gateway 2 and 3 they understand only the Wi-Fi and the Zigbee technology only, and for range 4 it supports only Bluetooth, so it will be receiving the sensor packets with Bluetooth technology. The modified capillary gateway can service and permit a higher number of packets with different technologies in comparison with the conventional gateways that denies packets with other technologies. And this is also obvious in the second chart where the modified gateway has collected a higher number of packets. As for the power consumption, of course, the sensors are battery operated, and its activity should be planned whether to recharge in case the battery has decreased under a certain threshold. The sensor states include idle, transmitting, receiving, and sleep state. The residual energy chart, as shown, shows that the Wi-Fi sensors have consumed the most power since it transmitted more packets than others during this time interval. Here we measure the end-to-end delay, which is computing from the moment the packet leaves the source until it arrives at the destination. So here, as we can see, the average end-to-end delay for the packets received at the gateway modified during the interval of 2 seconds, the first 2 seconds, the blue points are for the capillary gateway modified, and it did not exceed 0.015 millisecond. However, between the 2 and the 3 second, the delay has increased than the other gateways, but it did not exceed 0.02 millisecond. In case we have applied the quality of service in order to improve the end-to-end delay for the capillary gateway number 1, which is the modified old technology gateway, we used a quality of service classifier that can sort packets and gives priority for the modified capillary gateway packets in order to be transmitted firstly. And this has resulted lower delay, as we can see in the second chart, as the blue data points have lower delay. For the jitter, as we can see, the jitter, of course, it has various forms, and such as the variance of a packet delay, and it is the difference between the delay of the packet for consecutive packets, as indicated in the figure here. Before applying quality of service at the modified gateway, the jitter was a bit higher. As we can see, the blue points are scattered than the other points. After applying the quality of service, the jitter is lower for the modified capillary gateway and higher for the other capillary gateways. For the conclusion and future work, the simulation results, as we have seen, it has shown enhancement in terms of the quality of service, network operation, and performance. The throughput has been enhanced by 27% in comparison to conventional gateways, and for the packets permitted at the modified gateways, it has exceeded the Wi-Fi gateway almost 3 times, and the Zigbee and Bluetooth gateways almost the double. Of course, also we have shown an improvement when applying quality of service for the end-to-end delay and the jitter. And for the future work, as we have mentioned in the solution framework slide, that there are 2 other tiers, but but these were not the scope of this paper. But these two tiers will be responsible and equipped with machine learning and artificial intelligence for the process of intelligent gateway selection, which will be based on the network behavior and condition, in addition to maintaining a secure protocol design. Thank you for listening. That's all. Bye bye. Goodbye.